within the beaker. So make a nice big beaker. And if you have multiple colors of pens or pencils, it's going to be helpful. At least have that on your desk, 2 different colors at a minimum. 4 would be best. But if you don't have that available, then just go with 2. Looks more like a flask, Emma. I'm straight down because you're going to need more space than that. Like an Erlenmeyer or something. All right, so we're going to start by talking about what this buffer looks like. We've been saying that a buffer is a weak acid with a salt with its conjugate, but we've never really looked at what that would look like on a particle level. So let's start by adding to our beaker. We're going to add acetic acid. That's the acid I'm going to use for our example. It doesn't have to be acetic acid because we've been doing lots of different weak acids, so any weak acid is fine, but acetic acid is the one I'm going to do. Now, what happens if I put acetic acid into water? What kind of dissociation do we get? What will we see in our beaker if we add acetic acid to it? Hello? I put acetic acid in water, and then it breaks up into what? Okay, so it breaks up into H+. Does it break up into a lot of H+ or only a little H+? Only a little because it's weak, okay? We're going to use the very technical term, a little, for that. What else does it break up into? Okay, I hear some of you mumbling. Thank you. C2H3O2-. And are you going to have a lot or a little of that? Only a little, okay? Because again, weak acids only dissociate a small amount. You saw in the quiz yesterday the answer to number 4, the percent ionization on that one, although that was a buffer, it was still a weak acid solution, was 0.28%. Okay, most weak acids is less than 5 typically, and some of them go down even that small. So we don't get very much of those 2 things. What else is going to be in this beaker as a result of putting acetic acid in here? Acetic acid, the actual molecules of acetic acid. And will we have a lot or a little of that? There will be a lot. Okay? Now, switch colors. This is the important color change. So for those of you that only have 2 colors, this will be your 2. Now we're also going to add to it our salt. For this one, I'm going to use sodium acetate. I could have used any type of acetate salt. And I just needed to have the acetate part in common. Now, sodium acetate, being a salt, being an ionic compound that's soluble, is going to dissolve and it's going to completely break up. What's it going to completely break up into? What ions will we end up with? Thank you. Na+. And what else? C2H3O2-. Now, how much of each of those am I going to have? A lot or a little? A lot, because it completely breaks up. So we'll have a lot of this and a lot of this. Okay? So those are the things that are floating around the beaker. We're not concerned with the reaction happening between these 2 things because they both have acetate ion. So if they were to switch partners, nothing changes. It's still the exact same substances that we had before. Now let's talk about in this beaker what's important to us, because there are some ions that are going to act as the buffer, and there are other ions that are going to sit around and do absolutely nothing. Anything that you only have a little of, we are not going to concern ourselves with. Anything you only have a little of, we're not concerned with, because again, if only 0.28% of it dissociates, that's hardly any ion in the first place. Okay, so that's not what the important part of this buffer is. So we have 3 things left that we have a lot of. Only 2 of them matter. Thinking about your salt here is a basic salt. In a basic salt, what ion, the cation or the anion, which ion matters in a basic salt? The anion. So we don't care about this sodium ion either. He is literally going to float around and not really do anything. What's left are the 2 parts of the buffer that matter. We have this C2H3O2-, and we have our acetic acid. The acetic acid is our acidic part of the buffer. And the C2H3O2 minus is the basic part. You don't want to say that the salt was the basic part. It was the anion of the salt that is the basic part. And what's going to be very important in the problems that I'm going to show you today is that when you start your problem, the first thing you should do is identify what the acidic part is and what the basic part is. Do you have to draw this whole beaker to be able to do that? No, you just look at your substances. This right here is the acidic part, and then this ion from your salt is the basic part. Whatever the common ion is, that's going to be your basic part. And you have to get that down. I actually suggest, and I will have you do in your problems today, that you literally write it down. You write acidic part and write what it is, basic part and write what it is. Because today, in what we're going to do, you have to take the right one to react it. And so if you don't know which one's the right one, it's going to get confusing. We don't want confusing, that's for sure. Now, any questions about what this buffer looks like right now? So this buffer's living his life at whatever pH he's at, probably somewhere around 5, let's just say 5. So he's at a pH of 5. Now we're going to come along and add either strong acid or strong base and see what happens. We know that the point of the buffer is to keep the pH the same. It can't stay exactly the same, but we're going to keep it as close as we can to what it was before. So let's add, we'll use HCl as our strong acid, but any strong acid, this is what you will do. So we're putting into our buffer, our beautiful, wonderful equilibrium situation, we are now adding HCl. If I add HCl, what ions will I end up with in solution? What does HCl break up into? H plus, and what else? Cl minus. And it breaks up completely, right? We don't get any HCl's. We have complete H plus and Cl minus. Out of those two ions I have up there in red, which one's the one who tries to change pH? Which one's the one that will affect the pH unless we do something about it? H plus. So we don't care about the Cl minus. He's like Na plus. They're just going to float around. If we take the water away, we'll have a salt. But that doesn't matter. Okay? All we care about is this H plus. This guy right here is going to try to change the pH of this solution. The buffer doesn't want to do that. The buffer says, no, I'm going to get rid of you. Now, he can't just kick him out of the beaker. He has to get rid of him by consuming it. What part of the buffer can consume an acid? Will it be the basic part of the buffer or the acidic part of the buffer? The basic, right? Acids react with bases and vice versa. So this one and this one are going to neutralize each other. Okay? Or I should say the basic part of the buffer is going to neutralize the H plus. And I say it that way because it's not going to get rid of all of the basic part. And I want you to write what resulting equation we get from that. So I'm going to do that right here. This is a part of the math. We have to show this equation that we're going to write here. So what we do is we say the H plus is reacting with the basic part of the buffer, which is C2H3O2 minus. What do we get when we put H plus and C2H3O2 minus together? Acetic acid. We get HC2. Now, this might seem counterproductive. We put in acid, strong acid. There were all these extra H pluses. That was going to change the pH, so the buffer attacked the H pluses and they got rid of them. But by getting rid of them, it made a new acid, made acetic acid. But acetic acid is weak. And does acetic acid dissociate very much? As with all weak acids, not very much dissociation. So yes, we will make the solution a little more acidic. That acetic acid is going to decrease the pH, but only by a little. Compared to what that H plus was going to do. That H plus was going to drop it drastically. If you had added that HCl to water, it would have gone from 0 down, from 7 down to less than 2. I don't really know exactly what the number would be unless we did math. Hi.
Sorry, the number didn't work that fast. Right, maybe just look at the...
Pause.
Sorry.
Do you have that slip still?
I
602. Did I do 480? I'm sorry. 680.
4664.
Yeah,
Okay.
sorry.
That's it.
All right, bye, honey.
Everybody.
Oh.
Okay.
Hi, Mr. Prey. I didn't get a chance to put the lab on the cart yet.
Can I do that or no?
Yeah.
Okay. I didn't interrupt because I knew it was story time.
We weren't telling stories. We don't do that.
That's what I heard.
Yeah. My cart is over by the back door and it's pretty empty. You're welcome to use that. I'm sorry.
I can use this one?
Yeah. My TA had to go take a quiz, so... You okay?
Yeah.
All right.
I got it.
Okay, so back to where we were. So where were we?
Might take everything.
Yeah, just take everything off the lab station. Yep, and you should have everything you need, and then you just give it back to me and I can put it away. All right. So we made acetic acid, the pH went down. Oh, that's where I was at. So if we added this much acid to water, it would have gone from a pH of 7 down to less than 2. We added to this one, what did I say before this one was starting at? In my made-up world, 5? Maybe it went down to 4.95. Okay, it only decreases a little bit. Now, like I said at the beginning of the period, this is going to be better supported when I show you the math behind it. You're going to see why it only goes down a little bit. But conceptually, we need to make sure that we can write this equation. Okay, and again, we don't have to draw a beaker to be able to do it, but hopefully the beaker helps visualize a little bit better for you. We have one more thing we have to do to this before we can move on to the math. Let's add a strong base instead of a strong acid. So if we add a strong base, we put NaOH in. What ions is this going to break up into? NaOH, what does it break into? Na plus and OH minus, and it is complete dissociation. So we're going to get Na plus and OH minus. Of those two ions, which one causes problems for pH? Na plus or OH minus? OH minus. So again, I don't care about this Na plus. This is all I care about, is that base, that ion that's been put into that solution. So that base is going to react with the acidic part of the buffer, which is this guy right here. Okay, and your equation that will result will be OH minus plus HC2H3O2. Acids don't eat H pluses, bases take them. So the acetic acid is going to give the OH minus an H plus. If you put H plus with OH minus, you just get H2O. And now the acid has lost its H plus. Just become acetate ion. So we have just made more of the basic part of the buffer. If we've made more of the basic part of the buffer, the pH is going to go up a little bit. But not as bad as it would have been if only hydroxide had been affecting the pH. So we're choosing, I guess you could say, the lesser of both evils. Okay, hey, let's see if I was right. Mr. Craig, what's the pH of blood?
7.35 to 7.45.
I said 7.38. That's pretty much in the middle. Huh? Pretty good. Okay. Well, I said 7.4, maybe 7.38. That's what I'm
Normally books will just say 7.4, but
Yeah.
depending on CO2.
Yeah. Depending on whether or not your body's making acids or bases, Mr.
Yeah, that's right.
That's right. Okay. Let's not make it.
Nerd talk.
Let's not let it make him feel like his subject's that important. Okay, let's take it down.
Hey, I know about Ken.
That's right. Mrs. Stram still will not admit that. But all right. So let's take this into the math portion of it. Did I give you your notes yet? No, sorry, I forgot that part. Now I want to show you what this looks like mathematically. All those equations that we wrote, we will still be writing on our paper. We're just not going to be doing it with a beaker. If the beaker makes you feel better, you could do with a beaker, I guess. But we're going to be more just showing what's happening sort of in a step-by-step manner. There are some descriptors up at the top of your paper, just a paragraph or two, talking about what we just talked about, so that you can go home and reread that, okay? But I'm not going to read it to you. We're just going to move right into the problems. And I'll show you how this is going to work for these problems. All right, so for the first problem, first of all, we see the word buffer. And what do we all do? Thank you, we smile, because the buffers mean Henderson-Hasselbalch equation, which means less work, which means less time, and more time to answer other questions on the AP test. That's how I think of it. So these ones will still be that case. The only issue is that what was the acid and base concentration initially is going to be affected. So we are going to have to change that A and that B that are in that equation to be able to figure this out. This first part, though, this is not new. This is the concentration of a weak acid, concentration of a salt. You should be able to determine that pH because we did that yesterday. So please go ahead on your paper. I'm not going to tell you how to do it. I want you to do it for yourself. I want you to figure out the pH of this buffer solution before anything has been put in. Okay, so this is just the buffer itself. Please note they've given you moles, but it's per liter. So these moles really are like saying molarity. Do you like my truffle-tree? Have you seen the Laura?
I have not,
Oh, that's
but I feel like I have not.
Hey, are you going to take the kids to go see Dr. Seuss? I mean,
Yes, right.
Us too!
You.
We're going to dinner? Okay, you're busy. It's okay. It's just awkward. All right. Okay. All right, so we get a pH of 4.74, but I know you all got that answer because you're all brilliant and wonderful and did fantastic with yesterday's lesson. However, please make sure that what I have written in green is up on your paper too, okay? Because you have to show that dissociation. I know most of the time it's one-to-one, so I know you're getting to the point where it feels frustrating, like I just don't want to write it anymore, but you have to, because if you don't, then the grader looks at that like you plugged in the concentration of the salt to be the base, and it's not the salt that's the base. It's the anion of the salt that's the base. So you have to make sure you show that, okay? And again, they can't do one that's not one-to-one.
If you get the right answer, are they gonna like go back and be like,
Yeah.
okay.
Yeah, the rubrics, and you'll see more as we get closer, and you'll start to see the actual rubrics, but yeah, it literally says a point for this, a point for this, a point for that. So yes, it's not just right answer, okay? That's why I stress all this work so much. All right, so let's go ahead and move on to the second part. So the second part, now to this buffer that has a pH of 4.74. It's going to try to keep that this whole time, but we are going to try to mess it up by adding 0.02 moles of NaOH. Now again, it's in a 1 liter container, or 1 liter of solution, I should say. So that's just going to be molarity. And what you're going to do is this. You're going to start with your NaOH. That's our first issue, is that we don't really care so much about NaOH. We care about the ion in NaOH that is going to try to change the pH. So we have to show that dissociation. Breaks up into Na plus and OH minus. And we have to show what the concentration is going to be of the ion that we care about, which in this case, when it's a base, is going to be the hydroxide ion. Remember, H plus tries to change pH, OH minus tries to change pH. The other ones you don't really care so much about. Okay, now that you know that the hydroxide is going to be the bad guy, we know we need to get rid of that one. So hydroxide plus something in our buffer. So what in our buffer is going to try to get rid of this hydroxide? Morgan, what do you think it is? And why did you pick acetic acid? Good, because this is a base and acetic acid's an acid, then we need to react those two. You wouldn't have picked the basic part because a base in a base is not going to react. Okay, we have to have something that will react. So the OH minus and the HC2H3O2, we're going to end up with water when that transfers, and then we'll have leftover acetate ion. So that right there is essentially what we did with the beaker. You can see it's a lot shorter to just do it this way. Okay, you don't have to be drawing all of what's going on. You just need to draw the part that pertains to the part that you're discussing. Now here's where the new math comes in. What I'm about to show you is going to look a lot like an equilibrium table, but it's not. Okay, it's called an ICE chart, some people call them. So an ICE chart looks like this. ICE stands for initial, change, and equilibrium. Okay, so what we're going to be doing is recording underneath each one of these what the initial concentration of that substance was, okay, before any of this reaction took place. So for the hydroxide, we figured that out right here. So the initial concentration for the hydroxide will be 0.02. For the acid, that was given to you in the problem. Okay, we figured out the molarity of the acid was 0.3. Does water have a concentration? Is water a solution? Can you dissolve water in itself? Maybe. Technically, but no, you can't. So none of this water column is going to matter, just like with the tables. And then this one right here. Now we're going to be making some more of this ion, but the original amount of acetic acid, acetate ion came from the salt. So you look back, this is going to come initially from the salt. So the concentration that we figured out based on that salt was also 0.3. Okay, now for the change. This is different than the tables. No X's, nothing like that. The change is very simple. If this buffer is going to do its job, how much of that hydroxide should be there in the end? None, right? If it's doing its job, it's going to get rid of the bad guy, the OH minus. So if I started with 0.02, then I know my change is going to be 0.02. I know I'm going to use up all 0.02 of it. And the ratio between these two reactants is 1:1. So if I use up all of this 0.02 of this, then I'm going to react away 0.02 of this one. So this one will also go down by 0.02. Notice I didn't use it all. If I did, we'd be way beyond the buffering capacity of this buffer. But I used some of it. And the concentration goes down to 0.28. What's lost on the reactant side is gained on the product side. So the ratio between hydroxide and C2H3O2 minus is 1:1. So if I lost 0.02 over there, I'm gaining 0.02 over here. And those are your new concentrations. This is the concentration of your acid for your Henderson-Hasselbalch equation, and this is the concentration of your base for your Henderson-Hasselbalch equation, and now we can figure out what the new pH is going to be. By the way, pKa in that equation never changes, because it's still the same buffer solution based off the same weak acid that you started with in the first place. So we're going to go back now and plug in to Henderson-Hasselbalch. So pH equals, what was the pKa on this one? 4.7447 plus the log base. The new base concentration, it was 0.3, now it's 0.32. The new acid is 0.28. Okay, we added a base, so we expect this pH to change a little in the upward direction. And if you notice, it does. But does it change a lot? 0.06, I mean, I know things are all relative, but 0.06 is not much at all. If you had added this much of that strong base to water, the pH would have gone from 7 to above 12. Okay, maybe even closer to 13. So 0.06, this buffer did a good job of getting rid of that hydroxide. Okay, yes, it made some more of the basic anion, so it did make it a little bit more basic, but a very, very good job of consuming. Questions? Let's do the acid. Now for the acid, we're not adding it to this one that we already changed. We're adding it back to our original. Okay, so we're adding it back to a fresh new buffer with a pH of 4.74. So go ahead and start. I want you to start the problem and see that you can get it going. You look at what you've been given. You're going to take your HCl and think about what you need to figure out in the HCl first. Okay, so our first concern is the part of HCl that matters, which is going to be the H+. No matter what strong base that was going to be the H+. That was going to matter. So, I say base, I think again. Strong acid. No matter what strong acid it is, it's going to be the H+. So the H+ ion concentration I care about is 0.02. That's what's being put into this buffer. That's what we need to do away with. So now take the H+ and see if you can figure out what ion we need to show it reacting with. So again, think about H+ being acidic. If it's acidic, it needs to react with the basic part of the buffer, which is always going to be the common anion, which in this case is acetic acid, C2H3O2-, or acetate ion really, C2H3O2-. And it's making some weak acid. From there you set up your ice chart. So 0.02 for your H+, which we got from right above there. Remember we went back to the pure new, brand new buffer of 0.3 and 0.3. So our acid concentration was 0.3, and then the salt concentration and thus the anion's concentration was also 0.3. Why? Why would you do this card?
I mean, I love it, especially my coffee.
Dr. Pepper.
If I didn't have you.
That's right. All right, so how much of this H+ are we going to have when this thing is all said and done? None. It needs to go all the way. So taking away 0.02 here is going to take away 0.02 from both of them. And it's going to make 0.02 of that product because the ratio is 1-to-1 for all of them. Remember, we don't care. Oh, this one doesn't have water. Never mind. So you end up with your new concentrations of 0.28 and 0.32. Your acid concentration and your base concentration. Now we just take the Henderson-Hasselbalch equation. pKa stayed the same. That doesn't change. And we plug in our concentration of 0.28 over 0.32. These pHs are all about that ratio. Okay, it's all about that ratio. So it's about affecting the ratio as little as possible is really what buffers are trying to do. Okay, they're trying to affect that ratio as little as possible. All right, questions? One thing I didn't say when we were in A, if you guys would look back to A real quick, A is a problem that you could very likely see on the multiple choice section of the AP test. They probably would give you the pKa because they're not going to have you take the negative log of 1.8 times 10 to the negative fifth in your head, obviously. But one thing they do want you to be able to do is the second part of that problem in your head. Because the second part of that problem is the log of 0.3 over 0.3. 0.3 over 0.3 is 1, right? And the log of 1 is 0. So if they were to give you the pKa in that problem, they'd be telling you what the pH was. Because if the concentrations are the same, then pH just equals pKa. The log of those two would have to be 0. So those types of things, they're going to try to make it seem like, make you want to freak out when you're taking the test, like, oh, I don't know how to take the log of the ratio in my head. But look at the ratio, because if the ratio is 1, then they do expect that you know that the log of 1 is 0. Okay, little things like that. And you'll start to see some example problems like that, too, start to come through. Yeah?
This is sort of tricky, I guess, but like how you use the within a 1 meter solution.
Mhm.
You have to show that.
That's a good question.
Do it later.
I would show it. Yeah, just to be safe. I'm going to always probably say that, just to show it to be safe, but yeah, I would show it. Because like I said, even with that salt stuff, if not, they could say that you didn't know, that you were plugging in moles instead of molarity. So I would show it. Others. Okay, we have one more that we will try. Actually, I don't want to show you because it's got stuff up there. Let's go ahead and look at the problem. Number 2. Now this one, the acid changed. It's cyanic acid, which we haven't seen too much of. That's not a very common weak acid. But they are going to try to throw those acids and organic compounds that you've never seen before. It doesn't matter. The only thing that matters to you is that acid and that salt have an ion in common, which you can see, the CNO- is their common ion. And that's all that really matters. Who cares what the ion is, just as long as it matches. So our acidic part of our buffer for this one is going to be the HCNO. And then the basic part came from the salt, but it's the anion because it's a basic salt, so that's the part we care about. So part A is yesterday's stuff. We just have the formation of our buffer. Go ahead and figure out what your pH is going to be. Again, we're in 1 liter of solution. We're in 1 liter of solution. As you're checking A, please make sure that you have the work for the dissociation of your salt. Ratio is 1 to 1. Yes, it is the same number. Yes, you have to show it. So I got my acid concentration from my acid in the problem. I got my base concentration from the anion of the salt. Got my Ka, plug that in for negative log to get my pKa, and you end up with a pH of 3.35. Okay, so that's what our buffer is. That's what our buffer is going to try to maintain, regardless of the fact that we are about to put in either a strong acid or a strong base. So questions on that first part? Okay, let's do the second. So the second one is asking you, actually I don't want to show you, the second one's asking you to take and add an acid to your substance. Our acid that we are adding is nitric acid. So start by deciding which part of the nitric acid is important to the pH. Which one are we concerned with? Hopefully you identified H plus as being the important part. And you need to figure out how to neutralize the H plus. So go back to what we wrote about the acidic part and the basic part and decide what was the basic part of your buffer. That's what's going to neutralize that H plus. Don't just copy the initial line there. Think about what you have. So initially, look at your strong acid, decide the H plus concentration. The weak acid and the salt concentration, which gives you the anions concentration, were listed in the problem. So once you get to the ice table part, you know the H plus has to go away completely. So you're going to lose both H plus and CNO minus in that ratio, 1-to-1. You're going to gain, because of the 1-to-1 ratio, that same amount. That gives you your two concentrations now that go back into Henderson-Hasselbalch. These are our new adjusted concentrations. Once this buffer did what it was supposed to do, which was to get rid of the H plus, this is what your concentrations are now, 0.095 and 0.155. When you plug all of that in and get your pH, what the expectation is, because we always want to check that and make sure we haven't made a silly math mistake. The expectation is that it went down, but not drastically. Okay, the expectation is it became more acidic, but not by a lot. So you can see here this one went down by 0.09, no, 0.11. So not a lot. Not a lot at all.
We don't have to write that stuff.
No, you can leave it like that. Yeah. That's really fine. Yeah, dude.
Do we go to two or three sig figs on this?
Look back at your original problems. It should still be based on that.
But like, what I'm asking is like, when you add the 0.015 mole, doesn't that bring it down to 2 sig figs, or do you keep it 3 so you can compare them?
You are so right. Does it just say 0.05? Oh, what does it say? 0.015 or does it say 0.0150?
It's 0.015.
Then it should be 2 sig figs. You are correct. That's just a mistake on my part though, because I really want you to be able to see that second decimal, or else sometimes it's hard to see the change. You know, too few sig figs on these problems make it hard to see. Yeah. So yeah, I need to fix that. Thank you. I will make a note. All right, questions on that one? All right, let's do another base one. Again, I want you to try it. I don't want to just tell you what it is. So you're adding a strong base, I believe, KOH this time. KOH. Do me a favor in the problem, just go back and throw a 0 on both the KOH moles and the HNO3 so that you're showing 2 sig figs, just so that you can see that effect. And then that way we'll be able to better tell. You may want to fix it. So what are you going to show me on the test? This side? Yeah.
Right off the end, you're just directing that it has the 1 liter.
As long as they can see that on the test.
Anyway, that would be fine.
Yeah. Okay. All right, so you should have broken up your KOH into K plus and OH minus. We care about the OH minus. So the 0.015 OH minus is our concern. We're going to react the OH minus with the acidic part of the buffer, which is this HCNO. That ends up making water, which we don't really care about. It's not going to affect any concentration, so therefore doesn't affect our equilibrium. But we do care about the CNO minus. So plug in those initial values. We went back to the original problem, not after what we did in B. So that would make an interesting problem, I guess. And then we got our concentrations, our new concentrations, once all that hydroxide ion is consumed. So the production of this basic ion is fine because we're getting rid of that hydroxide, which was really, really basic, was really, really going to affect the pH. That basic anion from the salt is just a little basic. It's only going to affect it a little bit because as we've been learning, those weak ones just don't have that much dissociation. So we do see a slight elevation in the pH, 3.46 for those that can't see down there. I'll move it in just a second. We do see a slight elevation, but it's not much. Okay, not much at all, especially considering we put in a strong base. Questions? Are you appreciating the Henderson-Hasselbalch equation more after this? For those of you that aren't, it's only because you haven't realized. Take a look at this problem. What we did all the way through to this part right here has to happen no matter what. From this point forward, if we didn't have the Henderson-Hasselbalch equation, we would have set up an equilibrium table and gone through all of that. Okay? So do we appreciate the Henderson-Hasselbalch equation? Yeah. Which is, again, why when you see a buffer, whether or not it says buffer or not, if it's a buffer, a weak acid with a salt or a weak base with a salt, you need to use this equation. Okay? It will make your life easier, and it is intended to do that. So as long as you understand what's going on, then you'll be able to use it in its correct capacity. All right, questions about any of it? Okay, there's 2 problems on your paper. I want you to go home and try, okay, so that you don't have me giving you little hints as you're doing them, and we'll check those tomorrow. You also have a second part to your homework tonight. You do have a video lesson for the last part of this chapter. We're a little behind. I wanted to get us back on track, so we're going to do a video lesson, and this is a great one to do the video lesson. So I'll put your head up. Because, you know how you enjoy them. Because it's all about just graph interpretation. It doesn't have anything to do with what we did today. This is back on titration, okay, finishing out about titration. And so this is a great one for us to do that way. I think the video is right around 15 minutes. They all seem to be 15 minutes. I don't understand. I guess that's when I'm like done talking. My throat starts to hurt maybe or something. I don't know. Doesn't happen in class. No sneeze this time. Never came.
Maybe that shows that every single lesson is 15 minutes long.
I think what it means is if I wasn't pausing, Matthew, if I wasn't pausing and waiting for you not to answer, then yes, it would take 15 minutes. At one point today during the lesson when I asked you a question and none of you responded to a very easy question, I just thought to myself again, I should just record all my lessons and sit in the back and play video games because it would be pretty much the same, right? Not for Morgan. Morgan's a good girl. Morgan answers my questions enthusiastically, and then everyone laughs at her, which I don't appreciate, Morgan.
I'm cute.
You are cute, and they are girls. You're absolutely But so you have the lesson to do, which again is just some graphical interpretation stuff that is super important. So AP tests love to ask about these graphs. And then what I gave you for homework, most of those homework problems that are on there come from old AP tests. That's pretty much what I pulled for that homework assignment. So you can see the actual application of that concept in them. So your homework for tonight, 2 equilibrium, or not equilibrium, but buffer problems, your video, and the titration homework. Please understand that between all of that, my guess, for people that are super understanding, can do everything quickly, we're talking a half an hour. For those of you that are slower, probably 45 minutes. Okay, so it is a longer homework assignment for tonight. Please plan accordingly. There is an email at the end of my lesson. Okay, so if you need to email me again, and I do promise that it will go in for homework points. Okay, there were 3 or 4 people on the last homework assignment who did not get those homework points. Okay, again, it's very important to me. We're not just brushing off titration curves. It is a